Okay, let's continue with a couple of other examples, and let's just clear this canvas. And so we have learned about three typical functions that are used quite often in economics. And the first one was a utility function. Utility function, I'm supposed to write utility function. Then we had like an S-shaped production function. S-shaped production function. And then we had like an inversely S-shaped cost function or total cost function. Total cost function. Okay, so those are three regularly occurring functions in economics, and I'll just stylize them quickly before we look at some examples. So a utility function is subject to the law of diminishing utility. So it looks something like this. So we have a good, let's call it X, and then we have the total utility, and then a total utility function looks something like this. So it increases but at a diminishing rate of return. When it comes to a production function, what we do is we have an input, like for example labor or capital or land, and we convert that input into output and call output, maybe that's X. Okay, and input is maybe something like labor. And then if we draw it, it typically looks like an S, which means the more labor we have, we initially have output growing faster than input, but then there's a point of inflection and it flips, and output grows at the lower rate than input, but initially the output grows faster than the input. And then when it comes to the inversely S-shaped total cost function, so what we do is we convert the output. We want to know how much does a unit of output cost. So we have on the x-axis again X, and then we have here total cost. But when it comes to total cost, there is typically a fixed cost share, which is independent of output, like having to rent an office space or so, or factory or machines. So there is like a fixed cost share, fixed cost. And then on top of those fixed costs, we have this inversely S-shaped total cost function. So that looks something like this. So initially our output grows faster than total cost, but then it reaches a point of inflection and the total cost grows faster than the output. Okay, so we already talked a lot about the utility function and the law of diminishing marginal utility, so that is pretty clear. So let's take a look again at this S-shaped production function. So if we examine each point, we see that initially the slope is very flat, but then the slope becomes steeper and steeper, and maybe somewhere there's a point of inflection, and then the slope at each point becomes flatter and flatter again. So that means down here, if the output of x grows faster than the input, how do we explain that? Well, economists explain that if you have more and more labor at a certain place, like a factory, factor labor can start specializing. And, two people can accomplish much more than what you can do alone. So, if you have a factory or if you have a garage and you try to assemble an airplane in a garage, well, then having more people will help you to specialize and increase output. So initially we explain that output initially grows faster than input with specialization gains. But then eventually we reach a point when people start standing on each other's feet and having more and more labor. It's still good, but now it increases output only at a lower and lower rate. Okay, so now let's take a look at the cost function, and you see that initially the slope is very steep and then it flattens out, and then maybe here there's somewhere a point of inflection, and then the total cost grows faster than the output. So if you think that each worker has to be paid the same salary or the same wage rate actually, but then if I hire more and more people at the same wage rate, but those people become more and more productive because they realize those specialization gains, well, then the output grows faster than the total cost, or the total cost grow at the lower rate than the output. But then we reach a point of inflection, and once people start standing on each other's feet and block each other also a little bit, then if I hire more and more people, but they don't produce again more and more because those specialization gains from the division of labor are being exhausted, then the total costs keep on going up and up and up. Okay, so but that's the idea. And so now what we want to do is to convert those utility functions into their respective marginal utility. So let's first draw here let's put another graph there. So here x, and now we have here, we looked at the derivative of the total utility function. So that would be the derivative dtu with respect to dx. And that is what we call the marginal utility. Okay, and here we have again input or labor. And now here we have the marginal output, which is basically dx, the change in output x, with respect to the input. Let's call it labor, just L. And that is the technical term for that is the marginal output or the marginal product. I just call it MP, marginal product. Okay, and then for the cost function, so here we have again x. So now we have the derivative of the total cost function with respect to x. Okay, and that is what we call the marginal cost, MC. Okay, so what we need to do is we need to examine how does the slope on every point behave. Okay, here the slope very steep, it always flattens, becomes flatter and flatter and flatter and flatter. So that just means that the marginal utility function is some kind of a downward sloping curve, because the slope becomes smaller and smaller. So maybe here the slope is plus 10, so that value will be a plus 10. What about the marginal product? So we start out with a very flat slope, but then because of the specialization gains from the division of labor, the output grows faster than the input, but then we reach a point of inflection and output starts growing at a lower rate than the input. So that means that the marginal product function has some kind of a maximum, maybe here, but it looks like an inversely U-shaped curve. So here's then the maximum, and then it maybe goes down again. So that would be the marginal product. And you see, we just look at the slope at every point. And for the marginal cost function, it's just the other way around. So here the slope is really steep, becomes flatter and flatter. Maybe here's now a minimum. And the marginal cost function looks some kind of an inverse, that's not good, maybe some kind of an inverse, not an inverse, like a U-shaped function. So this is a typical marginal cost function. Okay, so I hope that with this example you get a feeling for what a marginal function, whether it's the marginal utility or the marginal product or the marginal cost, what it represents. It represents the slope at every point of either the total utility, the total production, or the total cost function. Okay, so I'll stop here, and then in the next video we'll start looking at some numerical examples, and we start taking the derivative of these.